Hello, I'm Mr. Bob, and welcome to my Algebra 1 video series. This video covers Chapter 4, Section 5, titled Applying Ratios to Probability. By the end of this video, you will have reviewed the skills necessary to understand theoretical probability. Then you'll be reviewing how to find theoretical probability and also finding the complement of an event. Then you will move to experimental probability, where you will be finding experimental probability, and end up using concepts of experimental probability. If you'd like me to cover any of the topics in this video in greater detail, please leave your request in the comment section below. Please subscribe to this channel if you find the video to be at all helpful. Give it a like too. Oh yeah, thanks a lot. Okay, before we get started, I'd like to just go over a few definitions. You'll see them again in the slides of this video, but let's just kind of get them going in our mind so we can be thinking about them. The probability of an event, or P event, that's how we'll write it, right? Tell you how likely that something will occur is, right? How likely that something will occur is. That's what the probability is. Outcome. An outcome is the result of a single trial. Flipping a coin, the result is the outcome, right? Whether it's heads or tail, the result is either one or the other. A sample space. The sample space is all the possible outcomes of a trial. Theoretical probability. Theoretical probability, the P event, the probability of an event, is equal to the number of favorable outcomes to the number of possible outcomes. If you're going to have a coin, you can have a head or a tails. There are two outcomes, but when you flip it, you're going to get an event, an outcome, and it's either going to be one or the other. It can't be both. Okay, so it's the number of favorable. So if you're looking for heads, it'd be the number of favorable outcomes versus all the possible outcomes. Complement of an event. The complement of an event consists of all the outcomes not in the event. And then experimental probability. Experimental probability. The number of times an event occurs divided by the number of times the experiment is done. Okay, let's move on. Okay, objective 1, theoretical probability. The probability of an event, okay, P event, right? The probability of an event tells you how likely it is that something will occur. An outcome is the result of a single trial, like one roll of a numbered cube. An event is any outcome or group of outcomes. Let's example for that would be if you take a numbered cube, as they like to call it here, and you roll it, that's one event. But if you have a handful of cubes, say there you have 5 cubes and you roll them all at once, then it's the group. The event is every one of the numbers on all the cubes that showed up. So that's a group of outcomes, okay? The sample space consists of the possible outcomes, of all the possible outcomes. So here's how these terms apply to finding the probability of rolling an even number on a number cube. Okay, so what do we have? We have the event. And what is the event we're looking for here? The event says rolling an even number. That's what we want to know. What's the probability of rolling an even number? So the sample space is this, all the numbers on the cube. That's 1 through 6. Right? And what are all the favorable outcomes? The favorable outcomes is anything that gives us what we're looking for in our event, which in this case is 2, 4, and 6 are the even outcomes. Okay? So the possible outcomes for rolling a fair numbered cube, that means it's not cheating in any way, are equally likely to occur. When all possible outcomes are equally likely, you can find the theoretical probability of an event using the following formula. So the theoretical probability right here, theoretical probability, or the probability of some desired event, is equal to the number of favorable outcomes. That's what we desire, the favorable outcomes, to the number of possible outcomes, like we did on that numbered cube, right? If you want to say what are the odds of getting a 1 on that cube, there are 6 possibilities, right? But you only want one particular one. Well, here, look at this. The probability of rolling an even number is 3 divided by 6. The number of possible events divided by all the events, which ends up being 1/2. So that would mean that every time you roll that cube, it's 50-50, or 1/2 of the time it'll come up even or it'll come up odd. Going back to my original example, if it was 1 in 6, every 6 times, theoretically, every 6 times you roll that cube, a 1 should come up, a 2 should come up, a 3 should. It doesn't happen that way because of just the way probabilities work and the way nature works, right? You could roll 3 5s in a row. That's not going to happen very often, but you could. Okay. Okay, continuing with objective 1 here. You can write the probability of an event as a fraction, as a decimal, or as a percent. The probability of an event ranges from 0 to 1. So when it's 0, down here at the left-hand side, right here, 0, it's impossible for the event to occur. All right, impossible event. Rolling a 7 on a numbered cube of 6 sides, right? So you cannot roll a 7. And a certain event over here on the right-hand side is rolling a number less than 7 on a number cube. A certain event is you will always get 1, unless it stands up on its corner, you're always going to get a 1 through a 6 on that cube. And 0.05, or 0.5, excuse me, equally likely and unlikely. So that means it could be one, it could be the other. It's 50-50, as we like to say. And when we say 50-50, we mean here's 50 written in a percent as 50%. And here's where we get the 50. 50 possible yeses versus 50 possible nos, sort of a speak, right? So getting ahead when flipping a coin, it's 50%. Okay. Okay, example 1, finding theoretical probability. Let's look at this. A bowl contains 12 slips of paper, each with a different name of a month. Find the theoretical probability that a slip selected at random from a bowl has the name of a month that starts with the letter J. So what is it? The probability of such an event, right here, is the number of favorable outcomes. The favorable outcomes are months that start with the letter J, versus the possible outcomes, the number of how many months there are possible. Okay, so that equals 3 divided by 12. 3 is the number of months that start with J: January, June, and July. That's where we get the 3 from. And the 12, we get from the 12 months. So 3/12. And that, if simplified, is 3/12 is 1/4. So the probability of picking a month that begins with the letter J is 1/4, or 1 in 4 times. Okay, 1 in 4 draws. That's the probability. Okay, example 1, check your understanding. So if you've been with me before, you know this means I'd like you to pause the video and just try this on a piece of paper and pencil and paper. And when you come back, we'll work it together. I'll wait. Okay, here we are. Suppose you write the names of the days of the week on identical pieces of paper. Find the theoretical probability of picking a piece of paper at random that has the name of a day that starts with the letter T. So, what is that? How many days? So first of all, how many days of the week are there? Well, we know the days of the week are 7. We have 7 days of the week. And how many of them start with the letter T? Well, we know that there are 2, right? We have Tuesday and Thursday. So that would give us 2/7. And that is the answer to the question. 2/7 is the probability. So then we have P of that event is equal to 2 out of 7 possibilities. 2/7. Continuing on with objective 1, this is our third slide on this. The complement of an event consists of all the outcomes not in the event. Okay, so what does that mean? So the possible outcomes for rolling a number cube are 1, 2, 3, 4, 5, and 6. The outcomes for rolling an even number are 2, 4, and 6. Okay, so the complement of rolling an even number is rolling an odd number, 1, 3, and 5. So 1, 3, and 5 are all of the events that could possibly happen that are not in our original event that we're looking for. Okay, so the sum of the probabilities of an event and its complement is 1. So, okay, so if you have, look at it here, the probability of the event plus it's plus p not event. So all of the possible events and all the possible not events. So the 2, 4s, and 6s, and this is the 1, 3s, and 5s. When they all add up, it's going to be 100 or 1 or 100% of the possibilities that you can get. And so it's P of the not event is 1 minus the event that you're looking for. So if you take 1 and subtract, in our case here, 1/2, 2, 4, and 6 is 1/2 of the possible events. If you take 1 and subtract 1/2 from it, the complement of the event is 1/2. Okay, it's the other half. Example 2, finding the complement of an event. So here we go. On a popular television game show, a contestant must choose one of 5 envelopes. One envelope contains the grand prize, a car. Find the probability of not choosing the car. Okay, so the probability of a car is right here. The probability of picking a car is the number of favorable outcomes. So we know here that the grand prize is a car in one of the 5 envelopes, right? So one of the 5, that's exactly your answer. The number of favorable outcomes is 1, and the number of possible outcomes is 5, and we said it right here is 1 of 5. 1 of 5. That's exactly what 1/5 is, 1 of 5. Now, the probability of not choosing the car is 1 minus the probability of choosing the car. Well, if 1 of 5 is the probability of choosing the car, then 1 minus that fifth, 1/5, will leave you with 4/5, because 1/5 plus 4/5 is 5/5, or the whole 1. So the probability of not choosing a car is 4/5. Okay, example 2, check your understanding. There's a little thinking problem going to go on here. It says, in example 1, 2 above, you can pause the video, go look at 2 again if you need to, and come back. What happens to P of the event of P not choosing the car? What happens to that probability as the number of envelopes increases? So I'm going to let you pause the film and the video. When you get done, come on back and we'll talk about it. Okay, I'm assuming you've done that, so let's talk about it. So from the above, we had the probability of choosing the car, right, was 1 in 5. And the probability of not choosing the car was therefore 4 in 5, 4 of 5. Well, now what they're asking here is, as the number of envelopes increases, what happens to the probability of not choosing a car? Well, as this goes up, we're going to get 5/6, right? We're going to get 6/7, going to get 8/9, 100 101ths. How's that? So what's happening is this is getting closer and closer to 1. It's getting larger and larger. It increases, okay? The probability of not choosing a car gets tougher and tougher and tougher, or more and more probable. How about that? It makes it harder and harder to choose the car, but easier and easier to not choose the car. So it increases. it increases. What happens to the probability of not choosing a car? No, you're going to be more and more likely to not win the car. How about the lotto, so to speak, or those lotto games? They have millions and millions of tickets. Well, the more tickets they win, the less, unless your single ticket with your one number on it, the smaller the chances are of you winning that lotto, right? So that's kind of so you can think about that. Okay, let's talk about objective two, the experimental probability. The last was theoretical probability. Now we're going to talk about experimental. What's the probability actually as you're actually doing the events? The probability based on data collected from repeated trials is experimental probability. You can find the experimental probability of an event using this formula. And so what is it? The probability of experimental probability is the number of times an event occurs. It really sounds familiar, doesn't it? Divided by the number of times the experiment is done. So now you could have 1,500 items that you're going to test, and you're going to look at the number of events that you wanted and the ones that were like errors, things that are broken, right? Out of 1,000 toys, 21 of them were broken. So what you're going to look at the number of events. So 21 divided by 1,000, so to speak, or 100, or whatever the number is. We're going to see that come up in these next slides. Okay, let's look at example 3, finding experimental probability. After receiving complaints, a skateboard manufacturer inspected 1,000 skateboards at random. The manufacturer found no defects in 992 skateboards. That means it found defects in some of the remaining few, right? Looks like remaining 8 boards. What is the probability that a skateboard selected at random has no defects? Write the probability as a percent. Well, here we go. So the probability of no defects, P of no defects, is the number of times an event occurred. This is no defects. So how many times did it occur that there were no defects when they checked? And how many times did you check? Well, there were 992 skateboards checked and found to have no defects. So it's 992 is the probability of no defects when you divide that by the number of tests. It was 1,000 boards were checked and 992 had no defects. So that means that if you simplify this, that the probability is 0.992, okay, that there are going to be no defects. Or you could say 99.2% of the boards, or 99.2% of the time, if you draw a board out, you will not have a defect. So the probability that a skateboard has no defects is 99.2%. Okay, check your understanding on example 3. We're going to run our own experiment here, okay? So the manufacturer decides to inspect 2,500 skateboards. There are 2,450 skateboards that have no defects. Sound familiar? Find the probability that a skateboard selected at random has no defects. Well, again, what we say, you look at the number of what you're looking for. I'm looking for no defects. So they pulled out 2,500 boards, checked them. 2,450 had no defects. And we want the probability, P, of no defects. Right? No defects. So 2,450, no defects divided by the 2,500 possible, of the experiment, the number of skateboards tested. So that if you do the math on that, get your calculator, do the math, you'll find out that 0.98 is the ratio here of no defects to total boards, or 98% of the skateboards had no defects. Okay, example 4, using experimental probability. You can use experimental probability to make a prediction. Predictions are not exact, so round your results. I mean, you're predicting that something's going to happen. It's going to be you can round it to an even number, right? You'll see how that works out. The same manufacturer from above has 8,976 skateboards in its warehouse. if the probability that a skateboard has no defects is 99.2, that's what we just found in the last slide. That's the probability in that warehouse out of those 1,000 that they tested, that 99.2% will have no defects, because that's what they randomly checked. Predict how many skateboards are likely to have no defects. So again, they want the same prediction, but now they want you to use, we took a sample, we found out what the ratio of errors were or defects were or were not in that, and now they're applying it to a full stock. They could have 1,000,000 skateboards and they'd still use that 99.2. Okay. So so what is that? You take the number with no defects is equal to the probability of no defects, P of no defects, times the total number of skateboards, which we now know is 8,976 skateboards. So we're going to take 0.992. We have to convert it back to a decimal to do the multiplication. So 0.992 times 8,976. Okay, so here you substitute the decimal in for the percent. And then when you do that multiplication, you're going to get 8904.192. Well, you can start rounding this off. Let's just say that here when they did this simplify, they came back and we said it's approximately 8,900. You could have said 8,904 and you'd have still been rounding off and approximating, but about 8,900 boards are going to be error-free. And knowing that since you've guessed, it's kind of it's not an exact science, this probability, because you'll use 1,000 boards to come up with that number. You don't even know if 89.04 is the exact number. So that's why they say to round it. Okay. You're going to kind of just pick a nice even number. If you took of those 8,000 boards and took 1,000 of them and tested them instead of the 100 of them or whatever it was, I don't remember. I'm sorry. The greater number that you test, the more accurate the number that your percentage is going to be. And that's kind of what I'm getting at. So, okay. The approximately 8,900 boards will likely have no defects. Okay, example 4, check your understanding. So a manufacturer inspects 700 light bulbs. She finds that the probability that a light bulb works is 99.6%. There are 35,400 light bulbs in the warehouse. Predict how many light bulbs are likely to work. Okay, remember we talked about when you get your answer, you can round it, kind of like an estimate, so to speak. Make a nice even number out of it. Okay, so we want you to pause the video and try it. When you come back, we'll do it together. Okay, so what do we end up with? We know that there were 35,400 light bulbs, right here, 35,400. And we're going to multiply times the decimal equivalent of 99.6%, which is 0.996. You take the percentage and you divide it by 100 and you get the 0.996 in this case. And when you do that math, you're going to end up with 35,258.4 light bulbs. 0.4 light bulbs. Okay, that's what statistically, if you want to look at it that way, or mathematically in our probability here of this happening, is how many light bulbs should work. Okay, but you're going to round it, right, to something that makes more sense. And so when you do that, you can say we can round to hundreds, we can round to whatever you want, right? But in this case, we can round to hundredths. And if you do, the number is going to be 35,260 because the 8 will round the hundredths, 5 up to 6. So you're going to have 35,260. Okay? And so there it is, approximately 35,260 light bulbs will work. It doesn't say exactly. We don't know how many is going to work. It could be way more than that or way less than that. We don't really know. But statistically, if you look at it that way, based on our probabilities, that's what the answer should be, or at least close to that answer. Okay.